Okay, this is 6.3, number 48, obviously. And this is always a question that gets asked by the students. So this is good that you asked this, that you guys voted for this. So you have two different spheres, completely different sizes, in fact, and you're going to cut the top and bottom off of each sphere so they're the same height object. That's kind of the idea. And when you cut those top and bottoms off, you'll get these, as long as they're the same height, you get two completely different diameter holes. That's a way I think about this. I don't think about drilling two different size holes. Instead, I think, oh, they're just two different size spheres, and I want to make them the same height after cutting the tops and bottoms off. And so this is what you would get from that. Now, the part A says, guess which ring has more wood in it. Now, I have a terrible imagination when it comes to geometric shapes, so I could not possibly guess as to a result here. So instead, I'm going to use mathematics to tell me what I should have been thinking. Some people can visualize the response to this, but I sure cannot. So let me go ahead and draw a picture of a sphere. And you guys all know my spheres look horrible, so give me a moment. All right, so I get something like this. I mean, I already had it drawn up above, so I didn't really have to do this. But I want to showcase the XY axis on here so that I can at least start mathematically thinking about this. And they say the height, the overall height of this is going to be h. So I know that this distance right here that I'm drawing in fact, well, I'll just draw it in there in black. That distance is 1/2 h. So it's not a full h there. That's just a half of it. And I want to find the volume. I think that's what they want, right? Use cylindrical shells to compute the volume. Great. So I want the volume of this resulting napkin holder. And so I'm going to do this by shells. So here I just take an ith slice here. And I want to know what's the volume of that slice. And in the end, what I'm going to do is double up the volume, the sum of the volumes, because I'm just looking at right now the volume of the upper half of this napkin holder. But in the long run, I want the full volume. So what I'll do is I'll just find the current volume of that slice. If I rotate that around, that would give me a shell. So we have a circumference, 2 pi times a radius. And then that shell will have a height. Right? And then, height. There's a T there. And then, let's see, radius or circumference, height, and then it has a thickness, and we can see the thickness is delta x there. Well, let's see. First of all, I'm going to go ahead and label my beginning and my ending as far as how my my stacks, my shells are going to go, right? From what x value to what x value am I going to do this? So if I look at this, they say we're going to drill a hole of radius little r through the center of the sphere, big R. So the radius of that hole is little r. The radius of the entire sphere is big R. So I happen to know, well, that's not going to help me with this radius. This radius from the central axis of rotation is just an x value, so I'll call it x sub I. And in fact, it doesn't help out with the height either. The height is a y sub I at that moment. So I get that. And of course, I'll need a relationship between the y right there and the x value right there. And that's not going to be terribly difficult because we know that x squared plus y squared is the radius squared of the large circle. So this tells me that y squared is capital R squared minus x squared. So 2 pi x sub I times, this will be the square root, because you're solving for y, not y squared. It's the square root of a capital R squared minus little x sub I squared, and then we have a delta x. Great. And now I know I can go ahead and compute the entire volume of this napkin holder by doubling up, because I'm doing the top and bottom halves here, doubling up the volume that I just created. So start stacking all those shells. Remember, each shell has a volume 2 pi x root capital R squared minus, oops, there's supposed to be a minus there, minus little x squared dx. And now we have the question, what are we computing from? From what x value to what x value are we doing these vertical slashes? Well, that's from x equals little r to x equals big R. X equals little r to x equals big R. And at this point, it's actually not too terrible. This is actually a fairly easy integral to do. So we might as well compute it out. This is going to be 4 pi. And then integral, again, x equals little r to x equals big R of x root capital R squared minus little x squared dx. And this is a substitution. I'm going to go ahead and let u equal capital R squared minus little x squared, or you can actually let u be the square root. You could do that too. It doesn't really matter. In fact, maybe I'll do that just for fun. U is equal to the square root of that. That will imply that that'll imply that u squared is equal to r squared minus x squared, and now that'll imply that 2u du is equal to a negative 2x dx. Or in other words, wherever I see an x and a dx, I will trade it out for a negative u du, because the 2's cancel. So because these 2's divide out, I will trade out an x dx for a negative u du. So that's what I'm going to go ahead and do here. So that integral will become a negative, because again, we're trading out the x dx for a negative u du. I'll go ahead and write the u du. And instead of a square root of r squared minus x squared, that is going to be just u, right? Because that's what a square root of r squared minus x squared is. And now let's take a look at what we're going from and to. So x started at little r, highlight that. So therefore, when you insert little r into our let statement, we get that u is starting at square root of big R squared minus little r squared. So let me write that in. U is starting at the square root of big R squared minus little r squared. Now, on the other hand, when you substitute an x equals big R into this let statement, well, that's big R squared minus big R squared, or 0. So that means our upper limit has changed to just being 0. And you should recall from Calc 1, the very end of Calc 1, if you have a negative right there, you can get rid of it by flipping the limits of integration. So I can write this as a positive 4 pi integral from u equals 0 to u equals the square root of capital R squared minus little r squared u squared du. And now I can just take the antiderivative. So that's going to be, almost forgot the 4 pi there, so 4 pi u cubed over 3, again from 0 to the square root of capital R squared minus a little r squared. And this seems like we are almost done. 4 pi, and then we have capital R squared minus little r squared to the 3 halves all over 3. It looks as though we're pretty much done, but we're not actually. All we have done so far is just computed the volume of a random napkin holder. But there is a little trick in here. So let me go ahead and go back up to this statement right here. I need a relationship between little r squared and big R squared, and that relationship is going to come from the following drawing, and this is where I think people might get a little bit lost. So let me go ahead and draw this in. I'm going to use this pen color here. Take a look at this triangle right there, okay? I'm going to draw it off to the side. It's pretty thick and ugly there, so I'm going to go ahead and draw it off to the side. But if you take a look at that big triangle, it's a right triangle. It's of height 1/2 h. If you look at the x distance here, well, I'm not drawing it anywhere except for right at the radius of the inner circle there. So this lower x value is just a little r. And then the hypotenuse here is actually the radius of the big sphere. And the radius of the big sphere is capital R. What this is telling me is that whenever we see a little r and a capital R together, we can actually relate them if they're being squared. This will imply that little r squared plus 1/2 h being squared is going to equal capital R squared. Or in other words, 1/4 h squared is the same thing as capital R squared minus little r squared. Now that might not matter to you, but that statement right there is huge, because that statement is actually right here. So we can take the capital R squared minus a little r squared and replace it with a 1/4 h squared. So I'm going to do that. And it's going to actually bring up a very important point here. So 4 pi over 3 times a 1/4 h squared to the 3/2. And I'll go ahead and simplify this. So let's see, that's going to be 4 pi over 3. The square root of 4 is 2, then cubed is 8, so times a 1/8. And this is going to be h cubed. And this simplifies a little bit, right? So this is going to be pi over 6 h cubed. So how does that change this conversation? Let's see, what does this all mean? Well, we've just computed the volume of a random napkin holder. And when we started computing it, I didn't tell you that we grabbed the large napkin holder. I didn't tell you that we grabbed the small napkin holder. I just said we have a napkin holder of major radius r and a hole that was carved out using radius little r. And so using that argument, or using that kind of setup, we went through and found out that the volume of that napkin holder will eventually be pi over 6 times the height of that napkin holder cubed. Notice there's no statement about the radius of the napkin holder there. There's no statement about the original radius of the napkin holder. So if I have two spheres, one is 10 feet in diameter and the other one is 6 feet in diameter, and I cut the tops off and the bottoms off symmetrically so that the resulting object, the resulting napkin holders, if I cut tops and bottoms and drill, the resulting napkin holders, as long as they're the same size, height, that is, then no matter how fat one is compared to the other, one will be fatter than the other. No matter what, their volumes are only computed using the current height of that cut. And they both have the same height. So scrolling back up to the picture here, both of these spheres have different radii. They have different inner radii as well, different drill holes and different size spheres to begin with. But their resulting heights are the same, which means their resulting volumes must be identical. And so this helps me answer part A. I can now say that the volumes will be the same. And that is how I would use mathematics to help me get past a conceptual stumbling block, because I cannot visualize those volumes being identical, yet they're equivalent volumes. And it's pretty astounding, but the mathematics shows that is true.